Hello students, in the fourth unit we will discuss about the transformations. So up to now we are considering the moving charged particle. When the particle is moving, the inertial frame of reference associated with that particle will also change. Let us suppose that this is one frame of reference S. When the particle is moving at a particular distance, then in order to define the position of that particle, we should assign another inertial frame of reference. So relative to fixed inertial frame of reference, we will define another frame of reference. There should be some transformation. So from this system to this system. So in electrodynamics, we transform several quantities. For example, if you have considered the position, here the position of the particle may be x, y, z. Here the position of the particle may be x dash, y dash, z dash. So up to now we have defined only three position vectors, or three r theta phi or r z phi in cylindrical coordinate system. So in this transformation we will define another coordinate called time coordinate, so in order to assign another inertial frame of reference. So this transformation can be achieved by four vectors. So in these transformations of all these electrodynamic parameters such as electromagnetic potentials and electromagnetic field vectors and the Maxwell's equation, all these we will define the four vectors. So this transformation is associated with a four vector. So our next topic is, I am directly going to the topic, the transformation of electromagnetic potentials. How we can transform the electromagnetic potentials with reference to a separate inertial frame of reference, and how this initial and the final potentials are varied, how we can transform for that particular charged particle. In this class we will define. So the electromagnetic potentials are A and phi. The mathematical relation which correlates this A and phi is Lorentz condition. So what is the Lorentz condition? Divergence of A plus 1 by c square dou phi by dou t is equal to 0. So this is the Lorentz condition. Here for the potential, this potential, that means vector potential A will have three components such as Ax, Ay, Az, or simply A1, A2, A3. So we will define the four vector as A4, which corresponds to phi. Right? First we will take the relation, the Lorentz condition, which have the both terms A and phi, and here A is the 3 vector, and we have added a fourth A vector called A4, which is in terms of phi, so that A and phi are grouped together. We will find out a 4 vector. That is, we can write it as AU comma I phi by c. This is the constant term. Like the retarded time, we write it as t minus r by c. So here u value is from 1 to 3, and the fourth vector is I phi by c. These are the 4 vectors. To prove that AU is a 4 vector, that is, we need to prove A1, A2, A3, A4. So first we will take the Maxwell field equation. So what are the Maxwell's field equation? Del square A is equal to minus mu naught J, and del square phi is equal to minus rho by epsilon naught. So the first equation is, for del square A1, this is mu naught J1. For del square A2, this is minus mu naught J2, and del square A3, this is minus mu naught J3. These are the three different vectors, and if you multiply this equation with I phi by C in order to get the fourth vector, then what happens to the second equation? So del square, since A4 is I phi by C, let us multiply the second equation with I by C, then I phi by C is equal to minus I rho by C epsilon naught. If you multiply and divided with C, then I C rho by C square epsilon naught. What is the value of C square epsilon naught? 1 by C square is equal to mu naught epsilon naught. So 1 by C square epsilon naught is mu naught into minus I C rho. So here if you observe these equations, these are del square A1 is equal to minus mu naught J1, del square A2 is equal to minus mu naught J2, del square A3 is equal to minus mu naught J3. So if you want to write down this del square A4, what is A4? A4 is I phi by C, then this minus mu naught I C rho will be taken as, where A4 is equal to I C rho. In this way, we combine these two equations and a common equation is derived from these two equations. So what are the two equations? From this, del square A4 is equal to minus mu naught A4. So commonly these equations are written as del square AU is equal to minus mu naught J, sorry, this is J4, where J4 is equal to I C rho. Here U value will start from 1, 2, 3, 4. This is the transformation of Maxwell's equations in 4 vectors. So the complete set may be written as del square AU is equal to minus mu naught JU, where U will start from 1, 2, 3, 4. Next one is how we can transform from one inertial frame of reference to another frame of reference for this electromagnetic vector potentials. So consider this AU. What is AU? Magnetic vector potential in one frame of reference, and AV is the initial frame of reference. So here we will consider a matrix called alpha UV. We will transform the magnetic vector potential from one frame of reference to another frame of reference by multiplying with a matrix called alpha UV, where alpha UV is a predefined. So we can write it as gamma 0, 0, I, beta, gamma 0, 1, 0, 0, 0, 0, 0, 1 minus I, beta, gamma 0, 0, gamma. So this is the fixed one. So alpha UV is equal to gamma 0, 0, I, beta, gamma and 0, 1, 0, 0, 0, 0, 1, 0 minus I, beta, gamma into gamma, where gamma is 1 by root of 1 minus beta square, and beta is equal to, as usual, we all of us know the beta value is V by C. So this is the Lorentz transformation of the magnetic vector potential. So we have transformed the Maxwell equations. Next our aim is to calculate what is A1 dash, A2 dash, A3 dash and A4 dash. Right. These are the simple conversions. So first we will calculate A1 dash. A1 dash means in place of u substitute 1, that is alpha 1v into AV. That is, so here v value will goes from 1 to 4. So alpha 1 1 A1 plus alpha 1 2 A2 plus alpha 1 3 A3 plus alpha 1 4 A4. So this term is alpha 1 1, alpha 1 2, alpha 1 3, alpha 1 4. This is alpha 2 1, alpha 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, 4 1, 4 2, 4 3, 4 4. So what is alpha 1 1? This is gamma A1 plus alpha 2 1 is 0. So this total term is 0. Alpha 1 3 is 0. This total term is 0. Next one is I beta gamma plus I beta gamma into A4. So in these both terms gamma is common, that is A1 plus I beta into A4. What is gamma? 1 by root of 1 minus beta square into A1 plus I V by C into what is A4? A4 already we have defined it as I 5 by C. So I into I is I square minus value. This is equal to A1 minus of V by C square into 5 divided by root of 1 minus beta square. So in one frame of reference, A1 dash can be calculated by taking the values of A1 in one frame of reference and 5. These are the constants. So this is A1 dash. Next, A2 dash. What is A2 dash? This is A1 dash and A2 dash. A2 dash is equal to alpha 2V into AV. So that is alpha 21 A1 plus alpha 22 A2 plus alpha 23 A3 plus alpha 24 A4. So all these terms are zeros, that is alpha 21, alpha 23, alpha 24. Only alpha 22 value is 1, that is simply A2. A2 term is equal in both the inertial frame of reference. Similarly, A3 dash. A3 dash can be calculated from this formula alpha 3V into AV. That is alpha 31 A1 plus alpha 32 A2 plus alpha 33 A3 plus alpha 33 A3 and alpha 34 A4. All these constants 31, 32, 33 are 0. Alpha 34 value is 1. So simply A3 dash value is equal to this is 0, 0, 1, 0. Alpha A3 value is only remaining all terms are 0. So A2 dash is simply A2 and A3 dash is simply A3. Next, A4 dash. So what is A4 dash? A4 dash is equal to alpha 4V into AV. That is alpha 41 A1 plus alpha 42 A2 plus alpha 43 A3 plus alpha 44 A4. What is alpha 41? Minus I beta gamma into A1. Remaining two terms are 0. Last one is plus gamma into A4. So take the gamma as common, that is A4 minus I, beta is V by C into A1. What is A4? What is A4? I phi by C. So I phi by C. In this also we have I by C. So take the common as I by C gamma of I phi by C. Here we have phi dash minus V into A1. So here A4 dash. A4 is I phi by C. Then A4 dash is I phi dash by C. So this can be written as I phi dash by C. So I phi dash by C. On both sides IC get cancelled. We get phi dash is equal to gamma is root of 1 by 1 minus beta square phi minus V into A1. These are the transformations of electromagnetic potentials A and phi. So what are the transformations? A1 dash is equal to A1 minus V by C square into phi by root of 1 minus beta square. That is the first component. A2 dash is same in both the inertial frame of reference. A3 dash is same. Phi dash is equal to phi minus V into A1. V into A1 divided by root of 1 minus beta square. So this is regarding the transformation of electromagnetic potentials in another frame of reference. Next topic is Lorentz condition, small topic. Lorentz condition in covariant form. Covariant form means, what is the covariant form means in 4 vector form, that is right. What is the Lorentz condition? Divergence of A plus 1 by C square dou phi by dou t is equal to 0. So this is the Lorentz condition. So we can write it as divergence of A. So this 1 by C I am writing it as dou by dou t, dou of phi by C by Ct. So this C square is phi by C is one term and another Ct is one term. We know that divergence of A is nothing but dou A1 by dou x1 plus dou A2 by dou x2 plus dou A3 by dou x3. So we are writing covariant form means we are trying to convert this in a 4 vector form. So we all of us know that A4 value is I phi by C. So let us multiply the above equation and the denominator equation with phi. Then this can be written as dou of I phi by C minus dou of I Ct is equal to 0. What is dou I phi by C? This is dou A4. Dou A1 by dou x1 plus dou A2 by dou x2 plus dou A3 by dou x3 plus this is dou A4 by dou x4. So what is here x4? A4 is I phi by C and J4 is I0 and x4 here we have assumed it as ICT. So these are the transformations for the 4 vector. So combinedly this Lorentz equation in 4 vector can be written as dou of AU by dou x4 is equal to 0 where U is equal to 1, 2, 3, 4. So this is the covariant equation of Lorentz condition. So this is in 3 vector form. In 4 vector we will define the Lorentz condition as dou au by dou xu is equal to 0, or simply del dot xu is equal to 0, where del dot a is equal to 0, where del is dou by dou x1, dou by dou x2 plus dou by dou x3 plus dou by dou x4. This is a 4-dimensional divergence operator. So this is the covariance of Lorentz condition.